in a very similar way. So the kind of mathematics that you deal with there is just about the same.
Wow.
No memory. We're not going through all the mathematics. So please note that for your thermal profile, there's still going to be your X SFD. No, your XFDH. So the temperature that's coming in, or the flow that's coming in, will carry some temperature. Alright, yeah. You know, we need to get over this thing. Alright. Yeah. Thank you. So you will see that if we assume that this wall temperature is higher than the core temperature of the fluid that's flowing in, that wall temperature, being that the velocity is 0, will get heated up. So unlike what you saw in the previous lectures, where they sketched that lines with arrows, technically speaking, the temperature is not a factor. So you can't really have arrows in there. Right? So we represent the magnitude of the temperature using that straight line over there. That's the magnitude of the temperature. So the line, if it is longer, it represents that it's at a higher temperature. So this one is lower temperature. And since the flow is coming in, according to the velocity profile, it would also establish that kind of temperature profile. Right? So this is for the case where you have the wall temperature, right? The wall temperature here, the S here stands for the surface, is actually greater than your T temperature that's out there, where R, at the distance R over here. So again, for your pipe system, the labeling is that this is R, small letter R there, and from the axis all the way to the surface, that will be your R naught. And Y is actually defined as R naught minus R, and that Y is indicated by this small little arrow over there. So you will see that as the flow moves along the pipe, its temperature profile is also going to be fully developed in the following way. So this will be considered that is a fully developed temperature profile. And that sigma T over there represents your thermal boundary layer. So there's your sigma T. So note that the surface of the pipe can be under constant temperature. So this one here, everywhere in the pipe, that surface is experiencing a constant temperature. And if that constant temperature is higher than the core, that means heat is transferring into the fluid. And later on, we're going to hear more about when heat is transferring into the fluid, as there is fluid flow through there with certain mass flow rate. This fluid flow that's flowing through there will gain heat as well as it flows through, because the pipe is hotter. So that's where heat is transferring into the column of water that's flowing in there. So later on, we're going to see how we develop an equation for that. So the laminar flow in this case, for this T, this small little T over there, represents your thermal. So just now it was H, right? Just now it was H. That's for hydrodynamic flow. Hydrodynamic flow means it relates to velocity flow. Hydrodynamic. T here, thermal, refers to your temperature profile. So in this case, where your surface is at a higher temperature, so it ups around in that way. If your temperature Ts is less than your T, your ambient, then what's going to happen is that it's going to have this kind of temperature profile. It's very similar. It's very similar to your velocity profile. So right now it ups this way because the surface is hotter. It doesn't mean this is zero yet, it's just that it's shorter. Right? is not zero. So the Prandtl number is what you have seen before. So for a laminar flow, it's governed by this expression 0.05 multiplied by the Reynolds number for a pipe system multiplied by the Prandtl number over there. Now, similar to the velocity, the temperature field varies across the pipe section. And if we look at the average temperature, it's actually defined on the basis of the total thermal energy transported. So, what does that mean? The rate of your internal energy transported. Later on, we'll be making use of this symbol over here. This one refers to your rate. And when you see your rate, the E here refers to your internal energy. The dot over there refers to your rate. So it's very similar to your dynamics and control module, where you have a dot, that means it's called rate. What does that mean? It means this E dot T is actually equal to dt over det over dt. That is the meaning of rate. Right? So there must be time factor over there if you have a dot. Right? Now what I want to point out is this part over here. I'm going to circle it out. This part. Right? This part over here is actually your mass flow rate, if you still could recognize it. That's your mass flow rate. And the mean temperature is actually defined as equal to mass flow rate multiplied by CVTM. Right? And Tm is given by this expression. It's very similar to what we have solved before, so I'm not going to be deriving this expression over there. I just need you to know that later on we'll be making use of this expression over here. This expression says that the rate of internal energy transported is equal to mass flow rate multiplied by the specific heat. So this one is your specific heat. And multiplied by your Tm here, where M here refers to the mean or your average temperature, just like for your average velocity. Now, I wonder, could you remember this Q, small q, and then 2 primes? Actually, that refers to your Q divided by A, and Q is actually your heat transfer rate, and that has the unit of kilowatts, or if you want, you could write in terms of watts as well. So Q divided by A, that will be your heat transfer rate per unit area. Or sometimes you get to see some textbook would say it's called your heat flux. And it has the units of kilowatts per meter squared. So you have seen before the Newton's cooling law. Newton's cooling law. It says that your Q will be equal to HA, and delta T here refers to the surface of the temperature minus the mean temperature that's out there in the core part of it. So this surface temperature is going to be larger than your Tm. And if I were to bring this A over Q over A, you get H, Ts minus Tm. And this Q over A, we sometimes would use this Q double prime to represent that. Right, so these are all various symbols that you could see that's being used. So H here refers to your local convection coefficient. There's something about this word local. Remember I was saying that if you have a plate, at any section, your H value will be different from the other section. That's because there's flow is passing through. So that part that you say that is that H value, we call it a local heat transfer coefficient. That's the local, just that one single point. But we can't just use that one single point, we gotta use the average of that. So later on, you get to see this symbol as H with an over bar up there. So that over bar refers to the average heat transfer coefficient because we want to find out what's the average heat transfer coefficient over that surface area. So later on, we can solve that. So there's a question here. Note that Tn is never a constant and varies along the pipe. Why? Why do you think so? Tn is never a constant and varies along the pipe. Well, the reason is because the heated fluid flowing downstream will still continue to get heated along the pipe. Now what does that mean? We were talking about the pipe here. So let's say if the fluid over here has been heated up by a hotter surface over here. Now this surface is all going to be hot over there. So this heated fluid, as it flows down, is still going to get heated up further. Right? So the same as even at the core over here. So as you move further and further down that pipe, your temperature profile would increase in its magnitude. So if I bring you back to the slide before, this one over here, you can see that this magnitude actually increases downstream. So the temperature of that will increase because heat is transferring in radially as it moves downstream. That's because that surface is warmer, right? So you get transferred in there. Now, the set of notes provides 2 slides about the review of thermodynamics. Because you're in year 3, so you don't have to take year 1 and year 2 because of your Pauli consistency. And thermodynamics was delivered in Glasgow's year 2. So this slide serves as a review of what was